Hello from Stuttgart. So we're today presenting some applications from the field of chemistry and scientific visualization. And I prepared some examples. So the topic chemistry was a little bit challenging for me to get a few good examples, but I think I made it. So what I want to present you today is just give you a small introduction into the idea of visualization in chemistry, briefly retrospect into history of molecular structural analysis. Then I will go on with a short, briefly introduction to COAS, our software we are using here for scientific visualization. And the main part, I think, which is very interesting for those who want to propose projects, DNA projects, just what do we have to do to visualize your data with COAS. Further on, I will then present a few general modules from COAS and, as I mentioned, a few applications. And if you have the time left, I will show you a few molecules or molecule dynamic simulation. Not in our cave, I'm actually sitting in front of our tile display, so perhaps you have the time to do so. So, once upon a time in 1952, there was this lady, Rosalind Franklin, who was at her time a specialist in the field of X-ray diffraction for structural analysis. And what she did, so she was on improvement of the X-ray diffraction methods for the structural analysis of DNA molecules. And within her work, she created those pictures. So for just for the understanding, I just Googled it up a little bit. So this is just an overview of the method. So there's an X-ray tube in the back, just focusing the probe with a lead screen onto a photographic plate to get these images we see on the slide. So this was the method in 1952, and she was ongoing to get a better understanding of the possible structure of the DNA molecule. And further on, so these two guys, Francis Crick and James Watson, got somehow, some time, a short look on those pictures, and they started to make their own research on how this DNA molecule could look like. So the interesting thing, I found a sentence in his book, a book from James Watson, where he said, in place of a maybe two-dimensional pencil and paper, the main working tool were a set of molecular modules resembling the toy of preschool children. So what they did, they just used these tools to get a kind of 3D modeling technique to get a better understanding how these images, why the appearance of those images on the X-ray photographic plates. So then, I think you know that in 1953 they did a paper, published an article in parallel with Rosalind Franklin proposing confirming the structure of the DNA molecule. You can see the image from the paper on the right side. So beside all the research of the structural analysis, the interesting point for us is they used not two-dimensional pencil papers, but they used a 3D modeling technique just to understand the appearance of those images. And this is where virtual reality, a 3D modeling technique, gets into account. So we are using COAS at our place at HLRS when we're developing this software here. And COAS stands for the Collaborative Visualization and Simulation Environment. So on the left side you can see the map editor. So the map editor is the first choice when you're starting designing your application with CoWise. So on the left side of the map editor you have all the modules available. For example, you have the input-output module over there. You have, of course, I/O modules or also reader modules. You have the renderer modules, for example, OpenSceneGraph we are using. You have simulation tools and all kinds of other designing and designing tools for scientific visualization. On the right side of the application, you are generating the net. So, for example, on the top of the net, you can see some modules doing the input. So they are reading the files coming, for example, from the supercomputer. Then there follows a domain decompositing or compositing. So this does the work. So this gets the fusion of the data you want to render down there. So at the bottom of the net there's the renderer. And if you want to, on the right side, you can, of course, just add a little bit of simulation code. So inside CoWise, they can run an interactive simulation too. So the general data flow in CoWise is just some data generation or the reading of the data. Then, as I said, the domain decompositing or compositing, as you wish, the simulation, and then the visual post-processing and the rendering. So this is the basic of CoWise. On top of CoWise, there's OpenCover. So COVER stands for CoWise Virtual Environment Renderer. So OpenCover is some kind of the core of the virtual reality environment, doing the intermediate transfer between the user interfaces, the renderer, OpenSceneGraph in our case, and the core libraries of CoWise and the render libraries, core render libraries. So the interesting part is for us is the left one, first of all, so the flexible plugin system. So these plugins can be developed, can be implemented by our users individually. So if you have an idea of how to do special interaction, for example, or if you have to implement a special reading module, a reading plugin for your data in particular, then you can do implementation of this plugin system. So this plugin can be loaded online, so while the system is running in the K, for example, and just reads your data and getting your data into OpenCover or CoWise respectively. So OpenCover is capable of using all kinds of projection-based displays, virtual reality environment, or HMDs. Of course, as you see at the bottom of the slide, you can use this CoWise tool OpenCover for augmented reality too. We have a module for collaborative, computer-supported collaborative work. On the right side, this is the virtual reality broker, so it communicates with a master or server, just as you can see on the right bottom. For example, a cooperative session with a few video conferencing system, and of course you can manipulate or see and manipulate a model in a cooperative session. Then further on, we have some, I mentioned only some of these features. We have a volume rendering. Of course, we can read VRML, virtual reality markup language, and we are using user interfaces. I will just present in the next slide, and we are working on the improvement of the parallel rendering system, so that we can run using HPC resources for rendering too. So virtual reality user interfaces comprises of a hierarchical menu system, so you can just go through all the plugins and parameters online within the K, for example. We support concurrent interaction in this virtual environment, so every user in Cave or display or at his desktop can see the same interaction possibilities. The tablet user interface, as you can see it on this image, I think some of you have visited HLS last week, and we saw that tablet PC in our cave. We're using it very often. So with the tablet PC, you can use the tablet PC for input of text and numbers, because in a cave you have not a mouse or a keyboard as you have it on your desktop. So you have to choose another method of input for the input of text and numbers. We are supporting multiple devices at the same time, so you can use multiple tablet user interfaces at the same time. And of course, the virtual reality user interface and the tablet user interface are QT based, and there's an API available, so you can extend that menu system or user interface anytime. Now to the interesting part. I think I made a few slides just to get an idea how easy it is just to read in data for your application. So we're starting at the user domain specific modeler. So the user, for chemistry purposes, has his own application, for example, Chimera or Rasmol. So these are tools to design, to model molecules, and of course they can do some kind of visualization within the application. But if you now want to go further on to do visualization in a virtual environment, what do you have to do? So as I mentioned, you first have the first step. So you have to implement a reader module for your data if it is not available yet. So this reader module just makes the job getting the data from the application or the file data format and reading it into a shared memory system. So the shared memory system distributed, or our rendering cluster, for example, is used by OpenCover and basically reads the data, and with the data then it goes into the map editor we saw already, and then it can start rendering already. So the advantage for the users is that they can just use their software as they are familiar with. The implementation of the plugins is kind of easy, very easy, I think. So we can, for example, do this job easily within a TNA project. So if users propose to come with his data, his kind of data, the first step is we are going to do is implementing reader module to get his data into our software code-wise. As I mentioned, this would be the first step. The next step can be, for example, implementing of further I/O modules, for example, to get a write back into his application over there, so a write in his application. For example, if you do any manipulation to your molecules or adding some components or something like that. So if you did any manipulation to your data, of course you want to store them, and the best way would be to store them, if possible, in your original data. So further advantages are the use and development of interaction modules. So if you want to create a specific interaction with your models, with your data you're using, you can do this too. So some general visualization, some general tools, or what we can do with this tool in chemistry already. So the main part, as we saw on the first slides, was just gaining insight in the structure of molecules. So for example, this buckyball, this C60 molecule, long time ago there was this was a little bit tricky just to understand how this molecule structure is how this molecule is structured, how the atoms are organized in this molecule. So they tried all kinds of possibilities on a two-dimensional paper modeling tool. And for someday the researchers just saw a football lying around, and then he gets the hint, and he just came to the idea that the molecules or the atoms might be organized like a football you can see in the television. So this helps a lot just to get an insight of the 3D structure of molecules. And for example, on the right side you see the hemoglobin. So this is a molecule that binds the oxygen in your blood. So with the 3D visualization of this molecule, you can get an understanding, not in this two-dimensional visualization of course, but in 3D it's much more better to see, that the molecule just binds the oxygen molecule, its O2 molecule, when it gets inside this molecule. So it's kind of trapped inside the hemoglobin. And in the cells of the human body, for example, the cells just grabbing out the molecule again from the hemoglobin and doing their combustion molecule in the cell. So a further interesting part of visualization or virtual reality in chemistry is the possibility of navigation in large data sets. So some molecules or some molecule dynamics can get quite large. So our system CoWise is capable of rendering very large data sets. And as I mentioned before, we're working on a fast parallel visualization system so that we are capable really to render large data sets in real time. So on the next slide, you can see another possibility for animation and simulation capability in CoWise. This is used especially for molecular dynamics. I've rendered a few pictures out of the cave yesterday. For example, this is a distribution of molecules flowing through a spit. So you can see the distribution from the spits coming out, the molecules coming out the spit, just distribute to the other molecules. And of course we have, for example, a molecular dynamics simulation where two drops just merges to one drop. I don't know if we are, I have the videos, I can show you the videos if you want to. And the third example would be a condensation phenomenon. So the matter, the molecules just merge into one cluster of molecules in the middle of the image. And of course, so next example would be the interactive manipulation. So this is nothing special about this, so we can use the standard VRML manipulators as we are using them right now, just to manipulate molecules or to move structures, to cut structures away, erase them, or add further structures to the molecule. Of course, in a molecule there's a lot of more intelligence behind this modeling, so we are not capable right now to, for example, verify all the connections between the atoms and then the molecules itself within the molecule. So, but we can work on this within, for example, a TNA project. And of course, we can use interactive manipulation in collaborative sessions. So, if we want to connect, for example, two caves, so we can just join viewing the same molecules while interactively manipulating them. So a few more applications I can show to you. This is, for example, the computer simulation of Gaussian wave packets that just inserted in a graphene lattice. So this was a diploma thesis of a further student of mine who is now working at the University of Karlsruhe Institute for Technology. And he did the computer simulation on a huge cluster, and did the simulation in virtual reality. So this is the propagation over the time, and on the right side you see the propagation of the wave packet through a double split. So you can see behind the double split, so here's the two splits, their interference pattern. So the next one is volume visualization. So this is an interesting project, or has been an interesting project. Unfortunately, I didn't find the volume images, just the STL images. So what is this? This is a cathode of a fuel cell. So the researchers working on the improvement of the reactions inside the fuel cells. So the cathode is created by injection molding, and then it's a length about 2 to 3 micrometers, one cathode. And what they do, just to get an understanding how this volume looks like, so they are slicing this volume to very thin slices, and then these slices are scanned by an electron microscope and then get together to a 3D model. And with this model you can do volume visualization. So this is just a surface visualization, but then you can get a visual evaluation of the molding process, just to see how good your creation process is working. So next and last application, I think most of you have seen this application already in our cave or our tile display. So this is the simulation of the process of combustion. So there's the company Recon Services working at HLS, and they are using our cave, and they are simulating the furnace of a coal power plant. And with the furnace, of course, they are simulating the process of combustion within the furnace. So we can do the visualization of standard parameters, for example, the oxygen levels on this cutting surface. You can see here oxygen levels or temperature distribution, for example, on this ether surface representing temperature of, I think this was 1,600 degrees Celsius. And of course we can do particle tracing. So for example, these red particles are standing for the coal particles inserted by a burner in the furnace, and the blue particle is standing for the oxygen inserted by the burner into the furnace. And by simulating the whole furnace, the whole process of combustion, we can do the visualization to get the engineers a better understanding of the combustion process, and just to improve the efficiency of the combustion and of course the durability of the furnaces they are designing.